Another queuing model is a single server model with a finite or finite queue. So, if queue length is limited either by customer attitude or the physical facilities, then it is not desirable to use any of the earlier models. What we mean by queue length is limited either by customer attitude or the physical facilities. Customer attitude. Sometimes customers have a certain preference in terms of the number of queue or calling units in line before they actually join the line. Some would prefer that the length of the line be less than 5 people, while others are okay if the line consists of 10 people. Okay? So it depends on the personality of the customer. So that is limited by customer attitude. The other one is by the physical facilities. For example, if a particular boutique in a mall would suddenly announce a 70% off sale, then you expect a lot of people to come rushing into the boutique. But if the boutique can only accommodate up to 20 individuals at a time, then only 20 people can actually enter the facility and form a line inside the boutique. That is what is meant by limited by the physical facility. Now, sometimes you might see a particular scenario wherein there is a long line of people outside of a particular store. And yet, when you peek into the store, there is a very, very wide space still available to accommodate people. And yet, they are making people line up outside. That is because they are trying to manage the customer experience inside their facility. This is particularly true when you have high-end stores dealing to high net worth individuals. For example, if Louis Vuitton would declare a sale, they would still limit the number of people that they would allow inside their store, because if they would allow everybody to just go in, and then the customers would start pulling on the merchandise, then they might end up with merchandise that is destroyed prior to being bought. That's why they try to also limit the number of people inside their establishment, aside from the fact that they're managing customer experience. The assumptions of this model are identical to the basic single server model, except that the assumptions of an infinite queue capacity no longer applies. So usually what happens in such queuing models is that if the establishment knows that they can only accommodate up to 20 people at a time, for example, so once they have reached their maximum, then they would start giving out numbers to people outside who still want to go inside the facility. So let's say after 10 people have been served, then they would call in the next 10 based on the numbers provided. So if you have this type of scenario, then following are the statistics that you have to determine. First is the probability of 0 calling units in the system, or the probability that there is no customer in the system. That is P of 0 is equal to 1 minus the quantity lambda over mu, all over the quantity 1 minus the quantity lambda over mu raised to capital letter M plus 1, where capital letter M represents the maximum number of calling units allowed in the system, and the maximum queue length is M minus 1. Next is the probability of n calling units in the system, or the probability that there is a certain number of calling units in your system. P of n is computed as P of 0 multiplied by the quantity lambda over mu raised to your assumption for small letter n. Next is the expected number of calling units in the system, or L sub s, which is equal to lambda over mu all over the quantity 1 minus the quantity lambda over mu minus the quantity capital letter M plus 1 multiplied by the quantity lambda over mu raised to capital letter M plus 1 all over the quantity 1 minus the quantity lambda over mu raised to capital letter M plus 1. Expected number of calling units in the queue, L sub q is equal to L sub s plus P of 0 minus 1. Expected time waiting in line, W sub q is equal to L sub q all over lambda multiplied by the quantity 1 minus P of m. And expected time in the system, W sub s is equal to W sub q plus the quantity 1 over mu. Let's look at an application. A basic programming course includes a lab at which a student consultant is on duty to help students debug their programs. It can be assumed that no student will get in line for help if there are 3 other students waiting. Students arrive at the lab according to a Poisson process at an average rate of 4 per hour. Service times are exponential, and the mean service time is 10 minutes. Because the class is large, an infinite calling population can be assumed. So based on the scenario, what are the applicable queuing statistics? As usual, we begin the process by first identifying the given data. Lambda, or your arrival rate, based on the data, is 4 students per hour. Mu, or your mean service rate, is 10 minutes per student. So if you are to transform that value in terms of students per hour, then you would have 6 students per hour. So we are going to maintain the unit of students per hour. So with that, let's proceed with the first statistical requirement, which is your P of 0. So again, this is just a matter of substituting the data to your formula so long as you have chosen the correct queuing model to apply. So if you substitute the values that we have to this statistical formula, you would have 1 minus the quantity 4 over 6. Oh, plus the fact that your m here is equal to 4. Considering that there are 3 students waiting, right? Says there in the second sentence, it can be assumed that no student will get in line for help if there are 3 other students waiting. So 3 students are waiting and there is 1 student consultant. Therefore, the number of calling units that the system can accommodate at a maximum is 4. 3 waiting, 1 being served. Otherwise, the 3 would not continue waiting if the student consultant is available to provide service. So your m here is equal to 4. So again, substituting the data you have to the formula, you would have 1 minus lambda over mu, which is 4 over 6, divided by 1 minus, again, lambda over mu, which is 4 over 6, raised to m plus 1, which is 4 plus 1. And then simply compute. This would give us a P of 0 value equal to 0.383888625, or approximately 38.39%, or 38.4%. Okay, so this is your P of 0. Next on the list is your probability of n calling units in the system. In the previous queuing models that we discussed, we said that if there is no specific statement in the problem you are analyzing requiring you to compute for the probability of a certain number of calling units in the system, you can skip this particular formula. It's just that that one is not applicable for this queuing model. Why? Because further down the list of statistical requirements for this queuing model, for the third formula in this slide, the expected time waiting in line, if you would notice, the denominator portion of the formula requires the value of P of m. In our example, our m is equal to 4. Therefore, in order for us to solve for W sub q, we need the value of P of 4. And in order for us to determine that value, then we have to use the formula for P of n, wherein your small letter n would now be equal to the value of your capital letter M. So let's apply that. So your small letter n would assume the value of your capital letter M. So this would now be P of 4, which would be equal to P of 0 multiplied by the quantity 4 over 6 raised to your capital letter M, which is 4, considering that we are assuming that your small letter n is equal now to your capital letter M. P of 0 was derived earlier to be your 0.383888625. And computing the formula, then you would get approximately 0.0758298, or around 7.58%. So earlier, your P of 0 is the probability that there are no student in line. This time, your P of 4, which is 7.58%, represents your probability that your system is full. because your system can only accommodate up to 4 students, 3 waiting in line and 1 being served. Next requirement is the expected number of calling units in the system, or L sub S. Again, this is just a matter of substituting the data you already have and solving for the resulting value. L sub S would give us around 1.24170,617 students. Next on the list is your expected number of calling units in the queue. Again, substituting the data we have to the formula and solving for the value, we are going to get around 0.62559242 of a student. Again, the values we're going to get here are all averages. Next, expected time waiting in line, W sub Q. So if you substitute the values we have, your L sub Q was derived to be 0.62559242 divided by lambda, which is your 4, multiplied by 1 minus our P of M, which is 0.075823938. And then solving for the value, we are going to get 0.16923,077 of an R, which we have to convert to something more meaningful. So if you multiply this by 60, then you're going to get around 10.15 minutes, which is the waiting time in line for any student. And then the last requirement is the expected time in the system, or W sub S, which is equal to the value of your W sub Q plus the quantity 1 over mu. At this stage, remember that the W sub Q value that you have to use here is the one in terms of R, so that you would be consistent when you now make use of your mu value, which is 6 students per R. So if you substitute the values we have already derived, as well as the one given, then you're going to get here 0.3358974 of an R, which if you multiply by 60 would give us approximately 20.15 minutes. Which is quite logical because the difference between the W sub S value and the W sub Q, meaning if you subtract the W sub S value with that of the W sub Q value, then we get 10 minutes, which is the service rate per student. Okay. So 10.15 minutes is the waiting time plus the service rate would give you the waiting time in the entire system, which is 20.15 minutes. So again, these are all the values you're going to get when you apply a queuing model. It's up to you as to how you're going to use these values to make a decision. So let's say you ran a survey among the students who regularly make use of this laboratory, and if the students believe that the 10.15 minutes waiting time in line and the 20.15 minutes spent in the system are still acceptable to them, then there's no need for you to add another student consultant. But if these values are relatively slow according to their perception, then you can make use of these computations to justify the use of another student consultant. Okay? And then the last queuing model that I would discuss is models that have a finite or finite calling population. This model is used when the size of the calling population is so small that to assume it to be finite or finite would seriously degrade the usefulness of the queuing model. This is usually applied for situations wherein the only possible number of queuing units or calling units that can fall a line inside your facility is 5 or less than 5. This model assumes a Poisson arrival process and exponentially distributed service times. It can be applied to a multi-server queuing system or a single server system whose queue discipline is first come, first serve. Following now are the statistics to be determined. First, the probability of 0 calling units in the system, P of 0 is equal to 1 all over the summation from small letter n equal to 0 up to s minus 1 of capital letter N factorial over the quantity capital letter N minus small letter n quantity factorial multiplied by small letter n factorial multiplied by the quantity lambda over mu raised to small letter n. plus the summation from small letter n equal to s up to the value of your capital letter N of capital letter N factorial over the quantity capital letter N minus small letter n quantity factorial multiplied by s factorial multiplied by s raised to small letter n minus s multiplied by the quantity lambda over mu raised to small letter n, where capital letter N in this formula represents the number of calling units in the calling population, lambda is your mean arrival rate for each individual unit, s is the number of servers, and then we proceed to the next requirement, which is your P of n. P of n would now depend on your assumption for small letter n. If your small letter n is less than the value of your s but greater than or equal to 0, then P of n would be computed as P of 0 multiplied by capital letter N factorial all over the quantity capital letter N minus small letter n quantity factorial multiplied by small letter n factorial multiplied by the quantity lambda over mu raised to small letter n. Now, if your assumption for small letter n is less than or equal to the value of your capital letter N, but greater than or equal to the value of your s, then P of n would be equal to P of 0 multiplied by capital letter N factorial all over the quantity capital letter N minus small letter n quantity factorial multiplied by s factorial multiplied by s raised to small letter n minus s multiplied by the quantity lambda over mu raised to small letter n. And for any assumption of small letter n greater than the value of your capital letter N, that probability is always equal to 0. Why? Let's say there are 30 individuals enrolled in a class. And then I would ask, what is the probability that there are 35 students in this class? That probability is always equal to 0 because there are only 30 enrolled in the class. That is what is meant by for small letter n greater than capital letter N, the probability of your small letter n is equal to 0. And then you have the expected number of calling units in the system. L sub s is equal to the summation from small letter n equal to 1 up to capital letter N of small letter n p of small letter n. Expected waiting time in the system, W sub s, is equal to L sub s over lambda sub e, where lambda sub e is equal to lambda multiplied by the quantity capital letter N minus L sub s. Expected waiting time in line, W sub q, is equal to W sub s minus the quantity 1 over mu. Expected number of calling units in the queue, L sub q, is equal to lambda sub e multiplied by W sub q. Let's now look at this relatively simple example. In a certain computer facility, 3 central processing units are serviced by 2 computer engineers. Each CPU breaks down in a Poisson manner on the average of every 24 hours. Repair times are exponentially distributed, with the mean of 1 hour. We are being asked to determine the steady-state queuing statistics. So let's now again identify first the given data. Your capital letter N represents the number of calling units that can possibly form a line. In this case, the ones that can form a line would be the 3 central processing units to be served by the 2 computer engineers. So your capital letter N here is equal to your 3 CPUs. Next is your number of servers represented by the letter S, which in this case would be your 2 computer engineers. Next is your arrival rate. Okay. It says there in the second sentence that each CPU breaks down in a Poisson manner on the average of every 24 hours. So each is technically equal to 1. And then on the average of every 24 hours, so 1 over 24. So you have here 1 over 24 CPU per hour. And then that would be around 0.0416 bar CPU per hour. Next is your mu, or your mean service rate, which is 1 hour. So you have 1 CPU per hour. Okay. So with that, let us now proceed with the first statistical requirement, which is your P of 0. Again, this is just a matter of substituting the data you already have. So this would be equal to 1 over the summation from small letter n equal to 0 up to s minus 1. Your s is equal to 2, so you have 2 minus 1 as your upper bound. And then your capital letter N is 3, so you have 3 factorial over capital letter N again is 3 minus small letter n, quantity factorial, multiplied by small letter n factorial. At this stage, your small letter n is something that is not yet known because you're supposed to analyze this entire thing based on a movement from the lower bound of your summation symbol up to the upper bound of your summation symbol. So your small letter n would change along the way, but your capital letter N is a given, therefore it is something that is constant. Then you have lambda over mu, which is 0.0416 bar over 1, raised to your assumption for small letter n, depending on the analysis of your summation symbol, plus the summation from small letter n equal to the value of your s, which is equal to 2, up to the value of your capital letter N, which is equal to 3. And then again, you have capital letter N factorial, which is 3 factorial, over capital letter N, which is 3, minus small letter n, quantity factorial, multiplied by s factorial, so you have there 2 factorial, multiplied by s raised to small letter n minus s. So you have 2 raised to small letter n minus 2. And then you have lambda over mu, which is 0.0416 bar over 1, raised to your small letter n. Okay, so let's now expand your denominator. Okay. Let's begin with the first half. Let's begin with the assumption that the small letter n is equal to 0. So if small letter n is equal to 0, then you would have there 3 factorial over 3 minus 0, quantity factorial, or 3 factorial, and then multiplied by 0 factorial. 0 factorial is equal to 1. So you would end up with 3 factorial over 3 factorial, which is equal to 1. And then multiplied by 0.0416 bar over 1, raised to 0. So again, that would be 3 factorial over 3 minus 0, quantity factorial, multiplied by 0 factorial, multiplied by 0.0416 bar over 1, raised to 0. Plus, by virtue of your summation symbol, if your small letter n is now equal to 1, which happens to be the upper bound already, then you have 3 factorial over 3 minus 1, quantity factorial, and then multiplied by 1 factorial, and then multiplied by 0.0416 bar over 1, raised to 1. Okay, that is the first half of your denominator. Plus, let's now go to the second half of your denominator. This time, we're going to analyze that second half, beginning with the assumption that your small letter n is equal to 2. So you have there 3 factorial over 3 minus 2, quantity factorial, multiplied by 2 factorial, multiplied by 2 raised to 2 minus 2, multiplied by 0.0416 bar over 1, raised to 2. Plus, if your small letter n would now be equal to 3, which is the upper bound of that summation symbol, then you would have 3 factorial over the quantity 3 minus 3, quantity factorial, multiplied by 2 factorial, multiplied by 2 raised to 3 minus 2, multiplied by 0.0416 bar over 1, raised to 3. Then we compute. This would give us approximately 88.47%, the probability that there is no computer breaking down and falling in line. Next, in our list of statistical formulas under this queuing model is your P of n. Similar to the previous queuing model, you are also supposed to make use of this formula regardless of whether there is a statement in a problem asking you specifically to compute for the probability of a certain number of calling units. Why? Because the next formula, you have here L sub s equal to the summation from small letter n equal to 1 up to capital letter N. In our example, your capital letter N is equal to 3. So if you expand this formula, then you begin with small letter n equal to 1. So that would be 1 p of 1 plus 2 p of 2 plus 3 p of 3. Therefore, in order for us to compute for your L sub s, then we need the values of p of 1, p of 2, and p of 3 by using the previous formula. So let's begin with p of 1. For p of 1, that means your small letter n is equal to 1, which is less than the value of your s, which is equal to 2. But of course, greater than or equal to 0, therefore we're going to use the first formula for p of n. And then simply substitute the values that you have already derived, as well as those given. This would give us approximately 11.06%. Next is p of 2. For p of 2, your small letter n is now equal to 2, which is equal to the value of your s. Therefore, we are going to use the second formula to compute for your p of 2. Then again, substitute the data you have already derived as well as the ones given. You're going to get here approximately 0.46%. And then the last requirement is your p of 3. And since your small letter n here is equal to 3, which is equal to the value of your capital letter N, then we are still going to make use the second formula for p of n. This would be equal to approximately 0.01%. Okay. There is actually a shortcut for getting the value of your p of 3 in this case. Okay. Remember that the probability of all possible events, if you get the sum of those probabilities, you're supposed to get 100%, or 1 if you are dealing with integers. Okay. So, in this case, there are 4 possible events that can happen. First possible event is that none of the 3 CPUs would break down. Second is that 1 out of the 3 CPUs would break down. Third is that 2 out of the 3 CPUs would break down. And then the fourth possible event is that all 3 CPUs would break down at the same time. So if you already have the probability of your P of 0, P of 1, and P of 2, then to get your P of 3, you just have to get first the sum of your P of 0, P of 1, and P of 2, and then subtract that sum from 1 or from 100%. You're supposed to get your P of 3. Moving now to the next requirement, which is your L sub s, which is the summation from small letter n equal to 1 up to our capital letter N, which is equal to 3 of n P of n. So if you expand this one, as mentioned already earlier, beginning with your small letter n equal to 1, then you have 1 P of 1, or simply P of 1 plus 2 P of 2 plus 3 P of 3. And then substituting the values we have already derived, you are going to get an L sub s value equal to 0.12009,211 of a CPU. Again, we're dealing here with averages. Expected waiting time in the system. In this formula, we first have to compute for your lambda sub e. Lambda sub e is lambda multiplied by the quantity capital letter N minus L sub s. So substituting the data we have already derived as well as given to us, this would give us 0.11. And then we can already compute for your W sub s, which is L sub s over lambda sub e. So you have 0.12009211 divided by 0.11999614. This would be 1.000799978 of an R, which is approximately 1 R. Expected waiting time in line, W sub Q. This is W sub S, which is your 1 R minus 1 over your mu, which is 1. So this would give us 0 of an R. And then expected number of calling units in the queue, L sub Q, is equal to lambda sub E multiplied by W sub Q. But since your W sub Q is 0, then this would also be equal to 0. So in effect, what you have here is an ideal scenario wherein as soon as a CPU would break down, it would immediately be served, considering that your W sub Q is 0. No waiting time at all. Okay? So again, this is your ideal scenario. Now, of course, if you would like to test your system, particularly if you're trying to reduce operational costs, then you may want to test, what if I just maintain one computer engineer instead of the current 2 computer engineers? Would the resulting waiting times still be acceptable to me? Okay, so that is something that you can consider, considering that what you have at present is the ideal scenario. So those are the queuing models that we're going to discuss. In general, following are the steps in queuing analysis. The first step is the application of any queuing theory is to analyze carefully the real queuing system that needs to be modeled. This analysis includes determining the attributes of the calling population, the service facility, and the queue itself. Meaning you first have to identify the assumptions and the scenario you are analyzing so that you can properly match those assumptions against the assumptions of a given queuing model. If the available queuing models are deemed inappropriate, a decision must then be made on whether to resort to computer simulation to model the queuing system in question. And then the decision of whether to use simulation hinges on the following factors. Are the data necessary to build and validate the model available? Is the time necessary to develop the simulation model too long to affect the decision process? Particularly if the decision is required yesterday, then you wouldn't have time to test and come up with simulation models. Thus, the importance of the decision affecting the queuing system justify employment of a more costly simulation approach. Because based on my experience, when you do simulation, you have to have the computer programmer available. Sometimes more than one computer programmer. It has to be a team or even a separate entity in itself. And then the duration of testing, the validity of the model that they are going to develop would be quite lengthy depending on how accurate you want the model to produce results. So the cost of doing so should justify the use of that particular queuing model. The major advantage of queuing theory is that it is generally less costly to develop, run, and maintain a queuing model. Simulation's major advantage is that it can be used to model a much wider variety of queuing systems simply because it is not limited by the complexity of the mathematics. Because the formulas are provided there. Once you input that or set it up in a computer, even on an Excel, then you can simply change the variables and the values of those variables, and the computer can already generate the required values or statistical formulas. So that is your queuing models.